So in this video, we're going to look at how to answer the multiple choice questions at the start of the test on 5.2.2, so Boltzmann factor questions, and then also the question at the end, including the 6-mark extended response answer. The other video shows the answer to the shorter questions for part B, so tune into that video as well to make sure that you understand everything fully. So the first question with multiple choice questions has this graph here, which looks at the number of particles in moles, so 4 moles, 2 moles, 1 mole, of particles at different energy levels above some base level energy 0. And we're asked to work out the ratio of the number of particles in adjacent levels is given by the Boltzmann factor. What's the value for the Boltzmann factor for the solid? So immediately we notice this ratio. So we've obviously got this 2 to 1 ratio, so 4 to 2 to 1. So it's either going to be 0.5 or 2, so we can immediately cancel out these two here. And then we need to ask ourselves, what is it that's meant by the Boltzmann factor? Okay, the Boltzmann factor is it's a probability, isn't it? It's a probability that a particle has a given energy. And if it's a probability, it's always going to be between 0 and 1. So discount C, the answer there is A. And then we're told that the bar chart doesn't show the number of particles with 0 energy, or at the 0 level. So remember that we're quantizing, discretizing our energy levels here. So if we've gone from 4 to 2 and then 2 to 1, we're obviously decreasing by a factor of half. Work the other way, we're timesing by 2. So the number of particles with this energy here is going to be 8. So most of us got that, so the answer is 8. Question 2, we've got a graph of how the Boltzmann factor varies with temperature, and this is a really important graph for us to know about. It's specifically asked for in the specification. It's on the Prezi towards the end, and what we've got is a graph that increases and then decreases in gradient. So increase in gradient, decreases in gradient. So we've got graph here, value C is the correct one. It's not going to be a directly proportional relationship because it's exponential. It's not going to be a decrease, and it's not going to look like that. As we increase the temperature, obviously, we're going to increase the number of particles, the probability of a particle having a given energy. So we're going to increase the Boltzmann factor, and we kind of get this trend here. Question 3, we're told the following information, right? We're told that 300 Kelvin, a process has an activation energy which is equal to 10 times K, Boltzmann constant, times by the temperature, so times by our 300. So if we do 300 times 10, we end up with 3000 K. So our energy is 3000 K. That's our activation energy. We're then told the temperature is raised to 330 Kelvin. What statement about the rate of the process is correct? First of all, will the rate increase by 10% because temperature is increased by 10%? Secondly, will it increase by 10% because the mean square speed of the particles is increased by 10%? Will it increase by 9.1 times because of E over KT is 3000 K over 300K? It's 9.1, or will it be 2.5 times? So let's break these down one by one. So first of all, we've got this 10% because temperature is raised by 10%. Now, that's what we're saying is that the average energy is raised by 10% of the particles, but not the rate at which the process occurs. Remember, the rate at which the process occurs is linked to the Boltzmann factor, not just the raw temperature. So we're going to discount A. 10% because the mean square speed of the particles increased by 10%. Well, the mean square speed of particles has increased by 10%, but again, that's not linked to the rate at which the process occurs. That's the Boltzmann factor again. This idea of it being 9.1 times because E over KT is 3000 over 300 is equal to 9.1. Now, actually, this doesn't tell us anything about what happens when we increase the temperature. It only tells us about the ratio between the activation energy and the mean energy, which when we're at 300 Kelvin. So nothing about 330 Kelvin. So we're not going to take that one here. And then lastly, we've got 2.5 times because the Boltzmann factor has increased from E to the minus 9.1 to E by 2.5 times. And that's the one that's absolutely correct. So the thing we've got to remember here is that the rate of the process is proportional to the Boltzmann factor. If we remember that, then it can only be option D. Finally, we've got this activation energy E for conduction of a semiconductor diode is 0.14 electron volts. The operating temperature of the diode is measured to be 8.85 plus or minus 4 degrees C. We're considering the effect of this uncertainty causing the calculation of the Boltzmann factor. Which of the following statements is or are true? The percentage uncertainty in the Boltzmann factor is the same as in the temperature. That's not going to be true. What we've got here is that the percentage uncertainty in a power, and if you're saying that the percentage uncertainty in something that's raised to power is equal to the percentage uncertainty for the whole statement, you would agree with 1, but that's not right. So we can discount option 1, that's not true. Temperature should be expressed on the absolute scale in kelvins for calculations of the Boltzmann factor. Well, that's definitely true, so we like question 2. And then finally, the percentage uncertainty in T is 1.5% to 2 significant figures. Well, look, we can work that out. That's nice and easy to verify or not. So to do that, so we're going to do, we need to get our temperature in Kelvin, obviously. So temperature is 273 plus 85 is 358 degrees. 4 divided by 358, it's plus or minus 4 Kelvin, times 100 is 1.1%. So again, 3 definitely not true. So in that case, only 2 is correct. We're going to accept answer C. Right, for most of the questions, for the rest of the paper, apart from the very last one, you need to go to the other video, which I've posted on Google Classroom for you and linked to on YouTube. So question 5 in this paper is question 1 in the other video. Question 6 is question 2 in the other video. Question 7 is question 3 in the other video. It's a pattern here, isn't there? Question 8 is question 4 in the other video. And then we get on to question 9, which I'll go through in this video. So miss this page. So question 9, we're given a number of different bits of information. It's about the energy required to evaporate water or vaporise water. We've got this experiment where someone is measuring the change of the mass of a kettle as it boils. Lids removed from the kettle so water vapour can escape. We start out with a mass of 2.4 kilograms. After 2 minutes, we have down to 2.3 kilograms, and we're told the power of the kettle is 2,100 watts. And we're asked to work out the energy required for 1 molecule of water to turn to the vapour state. So, what do we need to do? We're told the molar mass here of water is 18 grams, and we need to work out how we get to this value of joules per molecule. So, we need to work out how much mass has been liberated or vaporised, what that means in terms of the number of molecules vaporised, and if we work out what the total energy is, then we can just do total energy divided by number of molecules. That's the energy for 1 molecule. So, for a change in mass of 0.1 kilograms, the moles evaporated is 100 grams divided by 18 grams per mole. So, number of moles evaporated is simply 5.56 moles. If it's 5.56 moles, we can look at how many molecules it is. So the number of molecules evaporated is 5.556 times 6.02 times 10 to the 23 is 3.44 times 10 to the 24 moles. Molecules worth of water have evaporated. To work out the energy per molecule, we need the total energy that's gone. So total energy is power times time. So 2,100 times 120. 2.52 times 10 to the 5 joules, and then it's just simply a matter of energy per molecule. 2.52 times 10 to the 5 divided by 3.44 times 10 to the 24 gives us 7.53 times 10 to the minus 20 joules. I've stated my answer to one more significant figure than to show that value. It's just good practice to show that you've actually worked it through rather than just copy down what they've written. We're then asked to think about the experimental technique and suggest and explain why her value of 7.5 joules times 10 to minus 20 joules is larger than the expected and accepted value of 6.9 times 10 to minus 20. And it's because of the underlying assumption that she makes that all the energy provided to the kettle is used to break bonds and evaporate water. Right? That's obviously false. There are other pathways that energy can travel. Lots of us wrote energy was lost to the surroundings, which, whilst true, is obviously a very vague thing to write. And you need to actually, in order to gain the marks here, write a specific energy transfer, right? A particular route through which that energy can go missing. So what else happens apart from water just evaporating? Well, the water is also going to heat up. So energy will also be used in heating the water, divided by mc delta theta. We can then work out that state also that the heating of the kettle body has occurred. So the metal itself that kettle's made from will heat up, and often, so this is that kind of one of your go-to routes. Energy will be lost to resistance or power dissipated due to the resistance of the components in the kettle. So electrical energy will be lost in the circuitry as well. So 3 different specific methods that energy is lost from the system. And importantly, you need to state one of those specific transfers rather than just evaporating, rather than just some energy lost to the surroundings, rather than just something vague like that, in order to get both marks. For the final question then, this 6-mark extended written answer, we're told the average energy kT of a particle at 293 Kelvin is about 4 times 10 to the minus 21 joules. This is less than the energy required for a molecule to go into the vapour state, however water does gradually evaporate. This question is then asking us to use the idea of particle collisions and the Boltzmann factor to explain why some molecules escape the liquid at this temperature and why the rate of evaporation roughly doubles when the temperature of a liquid is raised from 293 to 303. So we need to kind of, like always with these questions, if we can break down what are the different components of the question, then we're going to be able to make sure that we access all of the marks here. So we need to talk about particle collisions, and we need to talk about the Boltzmann factor, and use both those to explain why molecules escape the liquid. So that's 1 or 2 things, I suppose. And then also why the rate of evaporation roughly doubles. And we've got some numbers here, so we need to use those numbers. So we're going to have to do a calculation or 2 in order to get all of the marks. Now, with these 6-mark questions, if you don't address each mark or each part of the question separately, you're not going to be able to access 5 or 6 marks, so those level 3 higher level responses. It's all about breaking down the question to see what you can do. And actually, once you've done that, this is not a tricky question to do at all. So breaking it down, we're basically turning this into sort of 3 parts. We're going to talk about particle collisions. We're going to talk about what the Boltzmann factor is. So that's these 2 bits here ticked off. And then we're going to talk about or find the value for the Boltzmann factor at the 2 different temperatures. So this bit on particle collisions, essentially what we're doing here is we're going to answer the question, why do some molecules have more than average energy? And again, our language and our kind of bank of go-to explanations needs to include this in it. So why do some molecules have more energy than others? Right? And obviously it's because in the water these particles collide at random. I'm going to keep peppering my answer with this word random here. Okay? And what happens on those collisions? Well, on the collisions, energy is transferred from one molecule to another at random. And what we might find is that some particles will get lucky, another good term, and gain energy in a number of consecutive collisions. These particles then are going to have more energy than those surrounding them. So they're going to have energy which is well above the average energy of the particles, and if they've got lots more energy, they will be the ones that are able to break bonds and evaporate. In terms of the Boltzmann factor, well, the Boltzmann factor simply tells us the proportion of particles in a sample at or above the activation energy when we've got temperature T. Or you could state it rather than the proportion, you could say the probability of a single particle in a sample having energy at or above the activation energy. So you get a mark for giving me a statement describing what's meant by the Boltzmann factor, and actually you got credit for telling us the equation. So Boltzmann's factor is found by the equation F is equal to e to the power minus e over kt. So I've got there my actually pretty bog standard, I should be able to reel this out whenever asked to, explanation as to why some particles have more than average energy, and I've linked it to the probability that some will have more than average energy, and I've talked about it means that some particles are able to evaporate. So I've got that part of my question done. The next one is to find the Boltzmann factor at both temperatures 293 Kelvin and 303 Kelvin, and then give that the link to the rate. So first thing I need to say is that Boltzmann factor is proportional to the rate of evaporation. And so if that's true, then I just need to find my values and compare those values, and I can say that the ratio of those 2 values is equal to the ratio of the rates of evaporation at the 2 different temperatures. So I've got an activation energy that I've pulled out from the previous question of 6.9 times 10 to the minus 20. You could have used the 7.5 times 10 to the minus 20 that was worked out in the from the raw data from the kettle experiment, but we're also told that this is the accepted value. So there's my activation energy, the energy at which bonds break. And if I'm going to do K times T for each of the two temperatures, then for 293 Kelvin I get 4.04 times 10 to the minus 21 joules. You could have used just the 4 times 10 to the minus 21 given to us at the top here. And at 303 Kelvin it's 4.18 times 10 to the minus 21. I want the ratio E over KT. So E over KT, if I take this number and divide it by this number, I get 17.1. If I take the activation energy divided by that number, I get 16.5 at 303 Kelvin. And then I need to use that to find my Boltzmann factor. So E to the power minus 17.1 gives me 3.9 times 10 to the minus 8. E to the power minus 16.5 gives me 6.8 times 10 to the minus 8. And so my last thing I need to do here then is a comparison of those values. So the ratio of 6.8 to 3.9 is 1.75. So what we're saying is that evaporation occurs at about 1.75 times the rate at 303 Kelvin than it does at 293. So I've got some calculations and a quantitative comparison of my final values telling me about what happens to the rate. All of those things, good explanation, definition of the Boltzmann factor, comparison of the Boltzmann factor values at the two temperatures, get my 6 marks.